In this segment, I'm going to talk about what's called a charge double layer. This is really the science of what happens to charge near the surface of a solid that is immersed in a fluid of some sort. Um, and the concept of a charge double layer is really about so if I have a solid surface, typically the observation is that when I immerse that in a fluid, a charge will build up for various reasons on the surface of that solid, either from dissolution of species off the surface or agglomeration of charged things onto the surface to form what's called a Stern layer. But in either case, somehow you end up with a surface charge on things. And what we want to know is how that surface charge interacts with charge that might be floating around in a fluid. And typically what happens is in a fluid you have some ionization of species, or at least especially in aqueous fluids, but in essentially any ionic type fluid, there's some level of ionization in the fluid, even if it's just protons and hydroxyl groups in water. So in a fluid, most fluids, if there's no surface around, will have charge neutrality. They have to have charge neutrality, actually. And that means that at least in some portion of the fluid, you expect to find an equal number of positive and negative charges per unit volume. So the net charge density is zero. On the other hand, near a charged surface, what you'll find is that there is a preferential charge buildup in the liquid that is basically there to match the surface charge on or near the solid wall. And then there's a gradient, like essentially a gradient or a charge imbalance, not just on the wall, but in a small region near the wall as it transitions from a net charged liquid to the charge neutrality in the bulk. This happens for a whole bunch of reasons. So like I said, there can be ionization of surface groups. A lot of times this is on purpose, but sometimes not. So glass has hydroxyl groups that will ionize and leave behind positively charged silicon atoms near the surface. Sometimes people will put Cu groups near the surface, or COOH, where the H will preferentially ionize and leave behind negatively charged surface groups. There are some materials like sodium iodide, which will preferentially ionize one of the species of the solid and leave a charged region, like essentially a charged solid behind, releasing the other ions into the solution. And like one last example would be the absorption, the preferential absorption of some charged species onto the surface of a particle or a solid. And that's useful for a wide variety of different technologies, but it's especially important in biology where there are a lot of charged molecules going around. Colloids, things like milk, and porous media, so flow through microchannels, things like that. These tend to be important things that you can exploit. So let's try and visualize in terms of the number density of ions, what this looks like in a fluid. So, obviously, if I have two ion species in a fluid, there has to be some charge neutrality somewhere far away from the surface, let's say. So what I'll call that eta infinity, or the number density of ions at infinity for species I. Very far away from the surface, there have to be essentially an equal number density of positive ions as negative ions for charge neutrality, assuming that each ion carries the same elemental charge. But near the surface, where there's a charge buildup, one of the charges will build up preferentially to counteract the surface charge. And so, for example, if you have a positive surface charge, then negative ions will build up near that positive surface charge, and you'll have a region where there's some net charge density. So, for example, if it's negative ion buildup, then you'll have, the number density of the negative ions minus the number density of the positive ions would give you a net charge density.